Welcome, everyone. Today, we're going to talk about a major leap forward in AI evaluation. Specifically, we are diving into video-based reward modeling for computer-use agents, a new framework for evaluating autonomous agents at scale using a model called ExeVRM and a novel technique called spatiotemporal token pruning. This is joint research brought to you by teams from USC, UW, MBZUAI, and Amazon AGI. Let's start by looking at the ultimate bottleneck in agentic automation. Right now, computer-use agents are scaling incredibly fast across different operating systems. But here is the problem: evaluating if they actually completed a complex user instruction remains unscalable. Right now, our evaluation funnel is manual, rigid, and often blind, creating a massive failure point. And if we can't accurately measure an agent's success, we simply cannot train better agents. The truth is, the evaluation status quo is failing us. Rule-based parsers might have high accuracy, but they have zero scalability because they require custom scripts for every single application. Relying on sparse screenshots is highly scalable, but it's context-blind. It misses transient dialogues and the causality of actions. Process reward models give dense supervision but are incredibly slow and rigid. That's why we are introducing the ExeVRM paradigm. This approach uses method-agnostic truth execution video, which captures full temporal causality and evaluates agents purely on observable interface states. But moving to video-based evaluation isn't easy. We face two massive roadblocks. Roadblock 1 is data scarcity. Public datasets are flooded with successful demonstrations, meaning there is almost zero negative supervision to teach a model what a mistake actually looks like. Roadblock 2 is computational overload. High-resolution trajectories are highly redundant. If you naively feed 100 frames of 720p video into a large language model, you will instantly exhaust your token budget and trigger out-of-memory, or OOM, failures. To solve the first roadblock, we achieved our first breakthrough, building the ExeVR53K dataset. We unified fragmented interaction logs from diverse sources like OS World, AgentNet, and ScaleCUA, and turned them into a consistent, step-level video representation. The result is a massive corpus of 53,000 high-quality video task reward triplets, covering Windows, Ubuntu, macOS, web, and Android environments. To get the negative data we desperately needed, we developed our second breakthrough, adversarial instruction translation. How do we teach a model to spot failures without expensive human labeling? We use a vision language model to synthesize hard negatives. By generating unpaired, mismatched instructions and stepping through the justifications, we yield contrastive signals that actually achieved a 100% human pass rate on our audited subsets. Now, let's address the compute challenge. We have a dilemma. Evaluating computer-use agents strictly requires 720p resolution to perceive subtle, transient cues like cursor shifts and tiny text edits. But the reality is that 98% of the visual tokens in these frames are redundant noise. Feeding 100 frames of 720p video into an LLM exhausts standard 80 GB of 100 GPUs instantly. We realized we had to aggressively prune this noise. This brings us to spatiotemporal pruning, starting with space, or spatial token pruning. Spatial token pruning explicitly removes visually homogeneous regions, think large empty desktop backgrounds, that contribute zero discriminative signal. This drastically cuts the token count per frame while perfectly preserving the critical, fine-grained UI layout that the model needs to make decisions. Next, we prune across time with temporal token pruning. Temporal token pruning suppresses tokens that remain unchanged across consecutive frames using cosine similarity. Instead of processing a static window over and over again, temporal token pruning reallocates the strict token budget entirely to meaningful state transitions and decisive GUI changes. When you put it all together, you get the ExeVRM pipeline. We take a user instruction and 720p video frames, pass them through our spatial and temporal pruning modules, and generate a highly compact token sequence, just 42% of the original size. We then feed this into a Qwen 3 VL8B backbone. Because it relies purely on external interface states, ExeVRM acts as a universal judge, outputting a binary success or fail, along with the exact span of the first error. So, how does it perform? In short, benchmark dominance. On our held-out ExeVR bench dataset, targeted video reward modeling definitively beats general-purpose VLM prompting. ExeVRM 8B achieves state-of-the-art results with 84.7% accuracy and a massive outperformance in recall at 87.7%. It completely outclasses models like GPT-5.2, Gemini-3 Pro, and Seed 2.0 Pro. Our ablations also proved something crucial about resolution and reality. Dense 720p video context is non-negotiable for accurate completion judgment. If you drop the resolution to 360p or rely on sparse screenshots, critical GUI causality is lost, and performance plummets. Pruning the 720p video is the only viable path forward. Beyond just binary outcomes, ExeVRM excels at pinpointing failure. It can identify the exact temporal window where an agent makes its very first mistake. As you can see from the temporal IOU scores, ExeVRM localizes errors much more precisely than Gemini or GPT. For developers, this means you can instantly debug trajectories, highlighting the precise errant click or missed validation. And it achieves all of this with radical efficiency. Joint spatial and temporal pruning reduces redundancy across both dimensions simultaneously. This keeps peak GPU memory well within limits and per-step training time low, making long-horizon reward model training highly practical on standard hardware without having to aggressively downsample your video. To wrap up, ExeVRM provides the missing link for computer-use agents, a scalable, model-agnostic evaluator that sees exactly what the user sees, at the resolution that matters. It offers universal compatibility, highly scalable cloud-native training, and frame-level temporal precision. Best of all, we are making this fully available to the community. The spatiotemporal pruning pipeline, the ExeVR 53K dataset, and the ExeVRM 8B weights are all open source. Thank you.